Hi guys, my name's Dion. I'm a student from Darwin studying a Bachelor of Engineering at Charles Darwin University. In December 2017, I had the opportunity to travel abroad to India to attend a humanitarian design summit delivered by the university's partner Engineers Without Borders Australia. As part of that program, we were provided the opportunity to interact with members of a developing community in order to identify possible human-centred design solutions. The following is a presentation of the design solution that we identified after spending some time with salt farmers out in the Little Rann of Kutch. So where is this Little Rann of Kutch? Well, it's a salt marsh located very near to the Great Rann of Kutch up here in the northwestern state of Gujarat, India. It's out here in the desert where an estimated 200,000 people leave their homes in the local villages each year for up to 8 months to come out to contribute to producing the estimated 14 million tonnes of salt produced in the region annually. Coming out to live in some fairly basic temporary constructed accommodation. So one of the first steps in the process for the salt farmers is getting access to the underground brine water, which involves the excavation of a well, the installation of a pump, and then pumping that brine water out into a network of pans to control the temperature and concentration of the salt in the water before moving it onto a large settling pan where solar evaporation takes over, crystallising the salt. It was while discussing the labour-intensive task of excavating their wells with some local salt farmers that informed us of an unknown gas that they sometimes encounter that'll claim the lives of between 4 and 6 salt workers annually. Some salt farmers that I spoke to mentioned that the gas's presence isn't widely known or understood within the community, and that as far as they were aware, no one had conducted any study to verify exactly what it was. But whenever people in the community had a direct experience with it, they became much more cautious of it. I was then shown this video, filmed at the start of the 2017 season, showing the process in which the salt farmers used to detect the presence of the gas. So the first time I saw this, I was fairly amazed at the extinguishing power of the gas. And the fact that this hole uncovered had such a defined line right at ground level where this gas was obviously sitting. But without the experience or the equipment to verify, we had to make an informed assumption that the gas present is likely to be carbon dioxide. And armed with that knowledge, we decided that working on a design solution to the build-up of this gas would be worthwhile exploring. Some early design considerations were made after some broad initial research into what commercially available products are already on the market for confined space ventilation. And while researching these solutions, we discovered many would be unfit for purpose due to the temporary nature of their design. The light-duty PVC ventilation trunking being the most obvious suspected point of failure, being out in the harsh environment of the desert, exposed to the sunlight, the mud, the dirt, the dust and brine water. Additionally, the cost for most of these systems is fairly high, so we wanted to see if we could come up with a design that could be put together from easily obtained low-cost parts that are already used or readily accessible through the existing suppliers to the salt farmers, and ultimately end up with a solution that would be more economically viable than these off-the-shelf kits that are available. One of the more important design considerations that we had to make was the way in which we would displace the gas that's building up in the wells. We concluded that the safest way would be to extract the harmful gas from the well rather than force any good air down into the hole, as that would likely just force that gas outward uncontrolled, increasing the likelihood of exposure to persons standing at ground level around the well. So the design our team came up with is assembled out of just a few easily accessed products, namely some low-cost PVC pipe with a screw-on end cap, which the salt farmers already have access to and use in the construction of their wells, that we're going to use as an intake pipe with some holes drilled in it to allow airflow, but limit the amount of dirt and debris that can be ingested into the system. Some low-cost suction hose, which again the farmers already as part of their solar pump system that they've got already use, but will probably require a larger diameter than what they currently use for pumping the brine water, which should still be readily accessible through their existing suppliers. An inline duct fan, of which there's many options available that could be sourced and tested that are suitably sized electrically to allow connection to the solar system that they already have installed. With many of these fans priced fairly well, coming in at around the US $30 mark. An exhaust pipe system, in which there's several design ideas already, would suggest that the most appropriate would be selected during testing, but the design we've chosen for our particular prototype exhausts the gas low to the ground, as the gas that we suspect is carbon dioxide has already been identified by the salt farmers as being heavier than air. So we've decided that releasing it low and away from people should be an effective means of safely limiting that human exposure. And finally, some various fittings and other hardware that will be required to assemble the components into the complete system. That shouldn't cost any more than $10 per unit. And thus allowing the entire design to be delivered at a fairly conservative estimate of less than $60 per unit, including an allowance for local labour to assemble it. Unfortunately, we were unable to purchase only a small quantity of the proposed 100mm PVC suction hose locally. So shown here is the alternative that we sourced, consisting of some black ag pipe between the intake pipe and the fan, and some white flexible internal PVC ducting for the connection between the fan and the exhaust. Putting together the prototype was actually fairly hassle-free. The much more frustrating part was coming up with a method in which we could test the design effectively. I started out by attempting to construct a small chamber from a tarpaulin and a drop sheet in my garage. This didn't prove very effective, so I switched to putting up a tent in my garage that worked much better at containing the simulated gas, but didn't simulate the conditions in the desert so well, with the wells having that clear open source of fresh air directly above it. Nonetheless, I think the prototype design has certainly proved successful. There's still a long way to go with the development of the design to construct and monitor some of the prototype designs to ensure they're fit for purpose in the field and ensure the service life of the equipment that we choose is adequate. Also, given that we've only made informed assumptions based on very limited research and the design being based off some fairly rough calculations, it's certainly not ideal. However, I do believe it makes a good starting point in which to build on. While I leave you with the last of the footage of the prototype in action, I'd like to thank you for your time and consideration of our human-centered design solution to the build-up of harmful gases in the salt farming wells in Gujarat, India.